All right, chemists, now it's time to look at example 2. In example 2, first we're going to figure out which species is oxidized, which one is reduced. I see that the Fe is going from an oxidation state of +2 to an oxidation state of +3, so that's losing 1 electron. And when I look at all the other species in question, I see that the manganese is changing from a +7 to a +2. You might need to take a minute to work that out. Now, I'm going to have you go through and write out the half reactions and try to balance the half reactions in acidic solution. So why don't you go ahead and pause the video and work out the half reactions. Hopefully you got the same balanced redox reaction as I did. Now this is a net ionic equation, and if you look at the original problem, it's a molecular equation. So let's see if we can figure out how to turn our net ionic equation into a molecular equation. Let's look at the Fe+2. Comparing that to the original reaction in the problem, the Fe+2, we know it had to have come from the FeCl2. So if I have 5 Fe+2s, that had to have come from 5 FeCl2s. Then let's look at the 8H+. Where did that come from? If I look at the original equation up at the top of the screen, that had to have come from the acid. So that had to have come from the HCl. So 8H+s are going to have come from 8 HCl's. Then where would the MnO4 permanganate ion have come from? That would have come from potassium permanganate. So those are the things on the reactant side. Now if we look at the product side, where would the Mn+2 have come from? Well, that would have come from MnCl2. Then where would the Fe+3 have come from? That would have come from iron 3 chloride. And because it's 5 Fe+3, I need to put a coefficient of 5. Let's check our balancing. I have, on the reactant side, I have 5 iron, 5 iron. I'm going to skip the Cl's for now. We'll come back to those in just a minute. I have 8 H's, I have 8 H's, I have Mn, I have another Mn, I have 4 oxygen, and I have 4 oxygens. Now, I have this mysterious potassium on the reactant side, and I also have these Cl's. So let's take a look at the Cl's. So 5 times 2 gives me 10 chlorine, and then 8 times Cl gives me another 8, so 10 plus 8 is 18. So far I have 18 chlorine atoms on the reactant side. On the product side, I have 2 from the MnCl2, and then I have 5 times 3 gives me 15, so that gives me 17. So I have a missing Cl and I have a missing K. So if I look back at the reaction at the very top of the screen, notice that one of the products is KCl. So the K from the reactant side is going to also be present as a spectator ion on the product side, and that's where that extra Cl comes from. So one of the 18 Cl's on the reactant side stays as a spectator ion on the product side in the form of quote-unquote KCl. So I'm going to write in KCl on that product side. I'm going to squeeze it here underneath the H2O plus KCl. So now we're going to rewrite this as a molecular equation. So my final balanced molecular equation is going to be 5 FeCl2 plus 8 HCl plus KMnO4, and all of that is going to yield MnCl2 plus 5 FeCl3 plus KCl. And if I check my balancing, let's first check the Fe's. We saw we have 5 and 5, so that's balanced. And then for my H's, we had 8 and 8, so that's balanced. For my manganese, we had 1 and 1, so that was balanced. For my oxygen, we had 4 and 4, so that's balanced. And then the Cl's, we said we have 18, and now because we added in that KCl, that's my 18th Cl, and then for potassium, I just have 1 potassium on each side. And I just realized that I forgot to write in the 4H2O on that product side. I forgot to copy that over. So there we have it. Here is our entire balanced redox reaction in molecular form. in acidic solution. Good job.